Hello and welcome. This is Universal Gravitation, Part 4. So we have our force formula, universal constant G times the first mass times the second mass divided by the square of the distance between them. This gives us the force between them. So object A and B are attracted to each other. Now, in the previous video, we found out that the acceleration due to gravity would be now in terms of the mass of the planet divided by the radius of the planet squared. So this is the first time where we see a relation between the universal constant and the acceleration due to gravity, the little g. On Earth, it's 9.8 meters per second square. Now that we have an expression in terms of the universal constant, what happens to things that we use with the little g? For instance, okay, we know the weight is now this, so mg will be replaced by this. What about mgh? You remember this form, right? Or maybe mgy in general. We call this the gravitational potential energy at height y measured from a reference point. So if a building, let's say you drop a penny on top of the roof of a building, it's going to speed up while falling down. And if the height of the building is h, and let's take the origin to be the ground level, y equals 0. So this is y equals h at that height. So in the beginning, it is mgh. In the end, it's 0. The potential energy decreases. Therefore, the change in the potential energy, U final minus U initial, is a negative number. Every time you go downward, that's the case. If you go upward, the potential energy increases. The potential energy, given potential energy at a certain y, depends on where you pick your origin. If you pick y as the roof level, then below that level, your gravitational potential energy will be negative, for instance. So it's a relative concept, right? It depends on y, it depends on where you pick your y equals 0, which you can call the reference point. Reference point. But this reasoning assumed that g was a constant, but now we know it's not the fact. So what happens if you consider falling from a really high building, or let's say a comet approaching Earth this way? It's millions of miles away from the center of the Earth. It's a distance or I away, you know, and it's on a collision course with Earth. It's going to hit the Earth one day. At that point, the distance will be RF, which is equal to R Earth, okay, the initial position and the final position over here. So what is the potential energy over there at the initial position, right? It's a comet. You can't use mgy anymore because g varies, all right? So we need an expression that has a coordinate dependence. In this case, the coordinate is the radial coordinate r, right? So along this line here, this is the radial coordinate r. And what happens when you're here, r away from the center of the Earth? What is your gravitational potential right there as a function of r? All right, to address this, let's remember how we came up with this mgy in the first place when we did work and energy. So one thing to do is, or as a starting point, would be to calculate how much work was done by gravity as the object is falling down, right? So there's a force acting on it, force, which is the weight equal to mg, and mg remains constant along the way and does positive work. So the displacement and the force are all in the same direction. They're both in the same direction. So gravity does positive work. W, gravity, is positive, and it is equal to mg times h. Now, when we did this, if you remember in class, I start with a general case. So this is the initial point, y equals y initial, and y equals y final, and here it is y equals 0. So the object goes downward, moves a distance of yi minus yf. So this height moves over a distance of yi minus yf. So that distance times mg, that's what we were doing really. Mg times y initial minus y final. This is this work. So we usually like things like final minus initial in physics. That's what delta is, right? So if you rewrite this as plot a negative and then distribute the mg, so you will have here mg y final minus mg y initial. And if you call mgy as your uy, this will be equal to negative u final minus u initial. In other words, negative of the change in the potential energy. And it's not really our topic today, but using this and the work energy theorem, which says that the change in the kinetic energy is equal to work. So delta K would be equal to negative delta U. And if you put that term on the left-hand side, you would end up with delta of kinetic energy plus, not delta here, just write U, K plus U, which we call the mechanical energy. E mechanical, that is 0. It's an energy conservation law. The initial and final values of the mechanical energy, which is kinetic plus potential, would be 0. Anyways, the bottom line is the work done is negative delta U. If you guys have seen calculus, now this is for university physics students, you know that force times dl. So in general, let's say you're moving from point A to point B along this path here under the influence of, or let's say you want to find the work done by this force, some arbitrary F. How do you do that? You consider the line element along this path, an infinitesimally long, well, very short, very small, length is infinitesimal, vector along the path. At this point here, imagine this tangent line. to the path. So along this tangent line, a very small vector. I'm going to draw it a little bit bigger so you can see it like this. That is the line element, dl. And this dl and f are not parallel, not necessarily. In general, there's an angle here, call it phi. Okay, so in this case, you can define the work done by F along the path from A to B, point A to B. This is defined as an integral from point A to point B, F dot dl. Dot means the dot product, right? So the dot product can be written as the magnitude of F times magnitude of dl times the cosine of the angle between the two. All right, so for this problem of falling object, well, the force is a constant, but if you apply this formalism here, what you want to do is write it as, okay, we call these I and F, right? So work done by gravity from I to F. Gravity would be equal to what? Now, the dot product requires two vectors here, F and dl. So in our case, okay, let me change colors again. The force here is downward on the object. Using unit vectors, you could write it as negative mg j hat, mg j hat. And dl is the line element vector along the direction of the fall, and that is dl equals, the coordinate we use is dy, is y, so it's going to be dy times j hat. Okay, so if you want to be exact, you may write negative absolute value of dy j hat. Just means it's pointing downward. If it was going upward, you would make this positive. Anyway, so the integral would be from y initial to y final. Take the dot product of these two, and then you get negative mg j hat dot dy j hat, right? So there will be a negative mg if you change the limits from yf to y initial. This will be equal to mg y final to y initial dy, and that would be mg y final minus mg y initial. Sorry, I put the wrong one here. Let me erase this. We already changed the limits, so this is y initial. Move pen. Try to move the pen here. Eraser. All right, so this is y initial, the upper limit, and y final, which is the same result we have here. But this way, now I can write the change in the potential energy for the comet problem, right? So the work done by gravity in this case will be, okay, now what coordinates am I using? I'm using r, the unit vector along the direction, let's call it r hat. R hat is defined as the vector r, the position vector from the center of the Earth, which I consider the origin, all the way to the comet. Let me use the red here. So this vector here is r, the position vector. Just divide it by its magnitude, and you get the unit vector in the radial direction. So the force I have now in magnitude is this, but in direction, it's pointing toward the Earth. So Fg as a function of r, position vector, in vector form is equal to negative g, mass of the comet, just m, times mass of the Earth, divided by r squared. And I put an r hat here. Okay, it means the force is attractive and it's pointing towards the Earth. All right, so sometimes you would change this with just r, and the denominator you would have r cubed instead of r squared, just in case you see it like that. Okay, so the work done by gravity while the comet is going from here all the way to the surface of the Earth will be this integral then. Integral from Ri to Rf. R force, negative g m comet times m Earth over r squared r. Take the dot product of this with the line element towards the Earth. That will be dr r hat. Okay, so just like this one, but now we have a dependence on r in the integrand. So keep writing. Now we have negative g m m e from r initial to r final, dr over r squared. Or change the limits again and make this positive. G m m e from our final is Earth's radius, re. Re to the initial position, ri, dr over r squared, which becomes negative g m m e 1 over r. The limits are radius of the Earth and the initial position of the comet. So finally, we'll have okay, now I'm going to do this. I'm going to keep the negative here, and g m m e divided by r I. Okay, minus g m m e over re, which was the final, and and swap the order, change the order, and add the negative sign here. So negative G M ME over RE, or R final, minus negative G M ME over R initial. So that I have this as the difference final minus initial. So what does it mean? It means now the new form for the potential energy, gravitational potential energy, is negative G M Earth over R. Okay, now compare this to mgy. Now, what are the differences? mgy, the little g, was based on the assumption that you're not moving over far distances, really short lab environment or from the building. But now you can use any size, like comets approaching Earth, or any celestial object, or communication satellite. It would work. Second, now you have the mass of the Earth in the expression. Mass of the Earth, and it's negative. All right, this is always negative. Now, just like you could take y to be equal to 0, that would be our reference point. Let's take our reference to be infinity. So when r is infinity, because of the 1 over r dependence, you will have 0. U will be equal to 0. That's our reference point, okay? So you bring an object from infinity all the way to r. The work done by gravity would be the expressions we found, okay? So that's the new expression. And does this agree with the old one, mgy, when changes in r is really small? Let me check that in the next video, and also see what happens to the total energy, or mechanical energy, let's say, this one. And let's write this in the new form and see how it applies to the motion of satellites and all that. Okay, I'm going to stop now.